So I've put together this web page to try to do two things really. The first is to try to explain um, the impact of filter coefficients on a digital filter. So I have this digital filter here with 5 delay lines, and we can control the coefficient values and see the effect on the frequency response. And the second thing is to try to get across how digital filters actually work. And they work on a very basic principle called destructive and constructive interference, which I'm sure you've seen before. So let me try to explain that first of all. And with this setup here, I have basically a digital filter in which these delay lines here are all turned off because I'm multiplying them by 0. Whereas this last delay line has a value of 1. So basically what I'm doing here is I'm adding just two waveforms together. I've got the input being multiplied by 1, and it's been added with this fifth delay line, which is also being multiplied by 1. And we can see those waveforms over here in the time domain, and by clicking on these select buttons, I can switch on and off the waveforms to see which ones are interacting with each other. Okay, so in this particular case, there's only two waveforms interacting with each other. We got the green waveform, which is the input delayed by 5, and the black waveform, which is the input being multiplied by 1. And I have this control slider here, which controls the frequency of the input. So basically, I have a sinusoidal input being applied to the system, and we're going to see what the output is. And the output is this blue waveform here. And what you'll notice is that at certain frequencies, the input will interfere destructively with the delayed version of the input. So again, the green waveform is a delayed version of the input. So it's delayed by 5 samples. And at this particular frequency, you see there's quite a bit of destructive interference. And the output is pretty much 0. If I moved it a little bit, it would be perfectly 0. It's difficult to get the slider to do exactly what I want though. But we can see that over here as well in the frequency response. So at a frequency of 0.2 pi radians per sample, we will get destructive interference. Okay, and if I move the slider along, increasing the frequency, we can see that we're getting some constructive interference. And at this frequency here, at 0.4 pi radians per sample, the two waveforms, the green waveform and the black waveform, are adding together to create a new sinusoid that's twice the amplitude. And we saw that in the frequency response here, where we can see at 0.2 or 0.4 pi radians per sample, the magnitude response, or what I'm calling the amplification factor here, is a value of 2. And as I move the slider along, you're seeing that we're getting constructive and destructive interference at certain frequencies as the waveforms interact with each other. So I get null here at the frequency of pi radians per sample, which is equivalent to the Nyquist frequency, which is the same as the sampling frequency divided by 2. Okay. What you'll see as I adjust these coefficient values, so let me reduce this one here, you're going to see the effect of the amplification attenuation, and the amplification and attenuation is being reduced as I reduce this number. But if I make it negative, you're going to see that where I was getting peaks before, I'm now getting nulls. So let me just switch that back again. And what you're going to see is, as I go back to +1, you're going to see that I get a peak where there was a null there. So you can keep an eye on 0.4 pi radians per sample, for example. Okay. So this particular delay line controls certain frequencies. We can amplify and attenuate certain frequencies with this delay line. If I looked at a different delay line, and let's take a look at x of n minus 3, and if I increase that, you're going to see that I can still get amplification factors of 2 and nulls at certain frequencies, but they're occurring at different frequencies. Okay, they're not the same as before. Okay, but it's down to the same thing. We are getting constructive and destructive interference. This time I have the sine waveform, which represents the input delayed by 3, being added to x of n, and we can still see the constructive and destructive interference occurring at different frequencies. So in this case, we're going to get a null at 0.33 pi radians per sample. Okay. We'll just take another look at one other value then. The second, this delay line here. And if I make that negative, what you're going to see is that we get destructive interference at low frequencies. So we kind of got a high pass filter here, and we'll get constructive interference at high frequencies. And if I switch it, if I make this go from a negative value to a positive number, we're going to see we get a low pass filter. Okay, so this one here also, like the others, controls different frequencies, and we can combine different frequency responses together by turning on and off different delay lines. So now I'm going to turn on the 5th delay line and the first one, and this is a type of low pass filter as well. So the key takeaway points are that these delay lines control or affect different regions of the frequency response. And the other key takeaway point is that digital filters operate on a very simple principle of constructive and destructive interference.